All right, hello. My name is Deven Hirsch, and today I'll be presenting an arc length calculator to you guys. All right, let's get started. So first off, what is the arc length of a function? Well, the arc length formula is a definite integral that is intended to essentially just approximate the length of a function f of x over a given interval a, b, given that the function is in fact differentiable across the interval. The graph of the function is divided up into an infinitesimal series of points, which are then plotted along the curve of the function from a to b. And then each pair of points across that breadth is then connected by a straight line, which sort of forms this newfound series of right triangles against the graph. And between each pair of points, with the drawn line acting as a hypotenuse, and the legs being the change in y and the change in x. And so between the points, given points x sub n minus 1 and x sub n, it's possible to invoke the Pythagorean theorem, a squared plus b squared is equal to c squared, to solve for the length of the hypotenuse c. And the sum of all the hypotenuses over the interval will be the rough numerical approximation for the arc length over of the function over that interval a to b. All right, and so let's just, I guess, consider some conventional pragmatic uses for this. So as you may have guessed, this is a very broad formula, and so it has a lot of practical applications. So for example, say you wanted to calculate the distance that you had to travel along a winding road from point A to point B, sort of imagining this as like a road atlas. So it's a 2D plane. So GPS pathfinding algorithms use satellite technology, and they have to analyze road networks. And of course, they have to tell you, like the distance between certain lengths of the road, where you are and wherever you want to go. And so this makes for a wonderful example for conventional use of the arc length equation. In order to accomplish this, you can imagine, the road is a 2D function over that interval, and then using the formula, you could get a reasonably accurate estimate of the road's actual length. And another example would be estimating the distance traveled by a space shuttle across a parabolic trajectory. Pretty much any scenario in which knowing the length of something that isn't immediately knowable, it's not straight, you can't just use a straight edge ruler to get its distance, that would be a good application for this formula. Right, so let's take a look at the problem formation. In order to program this calculator, I turned to Microsoft Excel. And the first step in the problem solving sequence is to take the Pythagorean theorem and through manipulation, morph it into the equation for the arc length of a function. So you start out and you divide by a on all sides, and you pretty much just work towards getting that c, the hypotenuse, isolated on that side of the equation. And so as you can see, that right there is the final result. C is equal to the square root of 1 plus b over a quantity squared times that a value. And then if we go ahead and change this up a little bit, we replace the variables in the equation and integrate, we get that derivative of the arc length is equal to the square root of 1 plus the derivative of y over the derivative of x quantity squared times that dx, the width. And then if you integrate, you get the arc length of the function is equal to the integral from a to b of the square root of 1 plus the derivative of the function squared times that dx. And then from here, let me move this. From here, we must select a value of n, which will represent how many subintervals of the interval AB, how many intervals it'll be divided into. And after specifying the lower bound A and B, the lower bound A and the upper bound B, we'll have to input a value for the dx, which is pretty much just the width of each subinterval. And then finally, we plug in the value of f of x, and the Excel calculator does a fantastic job at parsing all of this and applying the equations. And it'll print out a numerical approximation of the arc length of the function with a margin of error that's inversely proportional to the value of n. So pretty much the more subintervals there are, the more accurate your approximation will be. Okay, and the results here. Say we want to use my arc length calculator to find the arc length of the function y is equal to sine x from x is equal to 0 to x is equal to pi. So first, we'll have to recognize that the lower bound, in this case, a is 0, and that the upper bound, b, is pi. And then secondly, we'll have to decide on a value of n, which for the sake of this example, I decided to make it 12 just to get a good estimate. Thirdly, we'll have to assign dx an appropriate value. Since we chose 12 as our value of n, I decided to make the dx value equal to pi over 12. And as we can see here in the upper left corner of the spreadsheet, the a is 0, b is pi, n is 12. The dx is that pi over 12. And then we punch in the value of f of x up there. And then the resulting approximation is 3.816775, is roughly how long the curve is from 0 to pi. The objectives with calculating the arc length of a function is to get as close as you possibly can to the actual length of the graph from starting point A to ending point B. This example graph below demonstrates just how the formula works. It sort of visualizes the abstraction. You draw a polygonal path along the curve with n nodes in the path. You simply measure the length of each line by using the change in x or the change in y between a pair of points, and then the Pythagorean theorem and the distance formula. And like I said, the more n's you have, the more subdivisions you have, the more accurate the numerical approximation will be. Okay, and so an example that I pulled directly from my math lab, it asks us to find the length of the following curve. Y is equal to 3x to the power of 3 over 2 from x is equal to 0 to x is equal to 8. And to input such a problem into the calculator, we'll have to break it up in our input. We'll have to break that up into 4 parts. First is the function itself, which is 3x to the power of 3 over 2. We'll have to specify the a, which we know is 0, specify the b, which we know is 8, and then we'll have to decide on a value of n to subdivide our interval into equal-sized pieces. That's a very important part, which for the sake of this example is 8. And then the value of dx will, 5 steps, not 4. The sake of this example will be 1. That'll be the value of dx. And so now that we have our input, it's time to solve. As you can see, if I move this, we have 8 subintervals over here. We have the distances between each n value there, and then we have their sum total there, which yields the arc length approximation, which in this case is roughly 68.44779, which is only a few decimal places off the actual value. And so the conclusion is, after going through the hoops that this project has required me to go through, I can safely say that I have a renewed appreciation for the effort the programmers put into meticulously getting a calculator to actually parse, graph, differentiate, and integrate any particular part of a function that you, the user, will input. And I've had a lot of experience here just taking the derivative and integrating and using definite integrals. So I can really just say that this is going to be really, really helpful for me personally on the final exam, since of course there's going to be a lot of that. And then my sources are as follows.